Okay, it's 11:15. We'll get started. So make sure you are taking a look at the homework, starting to figure out in homework number 3 what you know and what you don't know. We're going to cover a lot of what you need to know today, but we will have a couple things on Friday that we need to talk about for the homework as well, so you can finish it on Friday afternoon. Remember, I have regular office hours tomorrow, and of course, I'm always available for an appointment. We just need to schedule that ahead of time, so I'm happy to chat. Now that we're in the semester, you should have an idea of how the class is going. You should be sort of used to my style. And so if something's not right, just look me up. I'm happy to do an office hours. That's no problem. And when is exam 2? February 25th, I think. So it's in like 2.5 weeks. We do it quickly. The second exam, it's a little fast because this unit is packed with information. So you'll see today that there's a lot of stuff going on that we're going to talk about. Kinetic equations, some chemistry. And so, I don't want to have weeks and weeks of material, and I don't really want to give you an exam right before the week before spring break. So we kind of do it quick, so then we can just ease into things through spring break and then hit it hard the second half of the semester. But keep taking a look at the syllabus and make sure that you're preparing yourself accordingly. There's only going to be 2 homeworks in the PLA. Then we're going to have exam number 2. So it's packed and it will come quickly. So make sure you're making preparation to be successful. And that exam is on a Friday. I couldn't fit it in any other time. And so if you have a conflict, just let me know. We can handle that. All right. Any questions, any comments, any questions on the homework? All right. So this is really important. This slide, you just need to commit this to memory. Again, we're talking about radical polymerization, which is an addition type or chain polymerization, generally using vinyl double bonds or some sort of carbon-carbon double bond. And so make sure you know this chemistry, make sure you know the monomers that can do this. You should have 10 or 15 of them, maybe 10 of them in your back pocket. Again, we're not going to go crazy on the nomenclature, but when I say styrene or when I say ethylene or propylene, boom, you should just know that. It should be right on the tip of your memory. So there are a couple chemical structures you have to memorize. And so make sure you know which ones go with radical polymerization. So we have initiation. We have to make radicals in the first place. We have propagation. So remember, propagation is where we increase. There we go. Increase molecular weight. We get molecular weight right here. By adding monomers to the growing chain. So make sure we talked about head to head, head to tail, the way we put the monomers in the chain matters, right? And then termination, we talked about 2 different modes of termination. And from the homework, I will ask you about different modes, or I will give you some clues as to what mode of termination dominates, or if the modes are equal, and then you can figure it out from there, because each type of termination has a different signature, and so you need to pay attention to those clues. So this is a really important slide, and this will help you. All right, where we ended up on last time was chain transfer, and so chain transfer is not any of these processes. It's a whole other process. And basically, the thing that you have to remember with chain transfer is that you move the active center to somewhere else. So the growing chain end, this is always, looks like the growing chain end, right? The radical is in the right spot on the most substituted carbon. There's a polymer before it. So it's a polymer chain that has a radical that's going to do something, add a monomer, terminate, or chain transfer. And then this thing that we call TA is our model chain transfer agent. And basically what's going to happen is that T is going to quench the radical on the growing chain end. So this chain, whoops, This chain now is not growing any further. Has its molecular weight, has its X bar N, that chain's all set. And a new radical species is formed that can form a new chain or that can do something else. But it's likely that that A dot is much lower molecular weight than the growing chain. And so chain transfer to a chain transfer agent, to a monomer, to a solvent always decreases the molecular weight. There's also chain transfer to a polymer, and we'll talk about that. But this is the one process that we're going to discuss today. Okay, so you really want to have this general diagram in mind, and then we're going to talk about specifics. Okay, so chain transfer to a monomer, solvent, initiator, these are all small molecules. And by small molecules, you know that I mean low molecular weight. Okay. Or we could add some specific chain transfer agent if we want to. You can also have chain transfer to the polymer. And so we were talking about this in the 2-minute office hours before class, is that you need to keep straight intra and inter. And the way I remember this is inter is like intermolecular force, even though we don't say intermolecular force all the time, we sort of slur it in our central Pennsylvania pronunciation. So intermolecular forces are between two molecules, inter between two molecules, dipole, dipole, van der Waals, etc. And so intermolecular chain transfer is between two polymers. So this is polymer 1. And this is polymer 2. How do we know that they're polymers in this diagram? They got the little squiggles, right? We could write out the repeat units if we want to. So this is a polymer right here because it's got repeat units and it's got an X bar N, but in our shorthand, those little squiggles mean polymer behind it. And we know that polymer 1 is the growing chain. Why? Why is polymer 1 the growing chain? How do we know that? It's got the radical. So, you know, this is polyethylene probably. You know, there's no substituted carbon in polyethylene. It's just CH2, CH2, CH2. So that's where the radical has to be. So polymer 1 is the growing chain N. Polymer 2 is just a polyethylene molecule with no growing chain that's just sitting there minding its own business. And then what happens is that this radical grabs a proton from polymer 2 and you get intermolecular chain transfer where now poly 1, there's no radical on that anymore, right? Because if you take a C dot and add an H dot, because we push one electron up from the single bond and one electron down, you've got 2 electrons between the carbon and hydrogen from the arrow pushing. And so polymer 1 is now quenched and it's just a polymer just sitting there. And when you take 1 electron going one way to make that covalent bond with carbon on polymer 1, you're left with a radical on polymer 2. So make sure you look at the arrow pushing. The arrow pushing is pretty easy in this unit. I mean, all we're doing is, you know, moving electrons, usually 1 electron one way or the other way, or moving protons around. So you want to understand what those half arrows mean and why you get a radical moving from polymer 1 to polymer 2. Yes?
Is it likely that the radical could just go back and forth between polymer 1 and polymer 2?
Sure. Yeah. Any chemical reaction, of course, will have an intermediate state where you climb up the energy barrier and the reaction can go either way. And lots of reactions go up to the barrier, rattle around, and come right back down. And so you can have back transfer, but we're talking about the forward direction. So we put in a single arrow in the forward direction, but you know from chemistry that all reactions have double arrows. It's just the rate constant of the forward reaction versus the rate constant in the back reaction. So it could transfer right back. We're going to talk about the situation where the radical transfers to polymer 2, and then they diffuse away from each other, and now that radical is stuck on polymer 2. And so you have a radical on a polymer chain. What are radicals generally going to do when they're sitting on polymer chains? They're going to react with something, right? And it just so happens that we're going to write the reaction with the monomer, because this is adding monomer. So if we bring in a monomer, we're going to basically make a growing chain from poly 2. And since we added N monomer, that's going to be a little bitty polymer with a degree of polymerization N that's growing off the side of that chain. And so you create through that process what's called a long branch or a long chain branch from intermolecular chain transfer. And this is a little bit hard to visualize unless you take this home, practice it tonight, write things out so you understand it. But basically you have your growing chain. Polymer 1 is this thing right here. The growing chain's on the radical. My pen is polymer 2. It's just minding its own business out in solution. There's no radicals on this guy. And they touch somewhere here, here, here. They probably don't touch right at the chain end, right? That'd be very unlikely for two polymers to come just like this. So generally, we think of intermolecular chain transfer as creating a radical somewhere in the center of this polymer 2, and then we grow a polymer from that. And that's why it's called a long chain branch. You change the skeletal structure. You go from a linear polymer, which mostly we've studied, to all of a sudden you put a radical right in the middle of the chain, and that starts growing, and that makes a long chain branch. And so it's important for you to know that intermolecular chain transfer to polymer causes a long chain branch. What it doesn't do is change the overall molecular weight distribution of the polymer. You will have to trust me on that. That is hard to illustrate. But intermolecular and intramolecular chain transfer don't change the molecular weight of the polymer because you're moving the radical from one polymer to the other polymer. And so your whole distribution of polymer molecular weights stay within the distribution. Yes?
So do intermolecular chain transfer always create long branches?
Yes, always. As long as in this step, you're adding monomer to that new radical, right? If that new radical dies or hits a chain transfer agent, something can happen. But most likely, you're synthesizing a polymer in the first place, right? So the most likely reaction is a reaction of a radical with a monomer. That's the most likely thing that's going to happen because the concentration of monomer is much higher than everything else. Yes?
Also, what if there's some sort of error within the actual creation of the actual long branch that turns from intermolecular to intramolecular? Is that at all possible?
Let's not get too complicated. Let's just learn these two. There's lots of things that are possible, but generally, we will stick with the basics and then you handle the exceptions in the higher division classes. Any other questions on intermolecular chain transfer? Okay, so make sure you can draw it. Make sure that you know it's between two polymer chains. Make sure you know it results in long chain branches, and make sure you know it doesn't decrease the molecular weight distribution of the polymer that you're making. It's a lot of things to remember on chain transfer. Intramolecular chain transfer is within the same molecule. We don't use intra a lot, and it's spelled weirdly, and so I just think about it as the thing that's not intermolecular because I know what intermolecular is. And so basically we have a very similar reaction where we have a growing chain end, right? This polymer is actually looking like this with the growing chain end right here. And sometimes this is called backbiting. Let's call it intramolecular chain transfer. And what happens is that the growing chain end radical is just transferred a few carbons back. We just put the radical right back there. And then when we add monomer to that radical, we have the original polymer that was there. We have this short branch, which is this right here. So this C4H9 is the short branch that we just bit off. And then this right here is a new growing chain. So intramolecular chain transfer, the growing end just bites back a few carbons and results in short chain branching when you add more monomers from that. And you can see that intra versus inter gives you different types of branching. And so if I tell you about branching, you know which process is most likely. Yes?
No, it doesn't go into the actual branching until that monomer is added.
It doesn't what?
Like, it doesn't turn into long branch or short branch until that monomer is added. Or it can't happen.
That's right. That's right. So you actually don't get a branch until you add more monomer because nothing's happened yet. But the most likely reaction is adding monomer. Yes. This step right here. Yeah. So if you count that, that's C4H9, right? So that branch, instead of drawing carbon, one, carbon, carbon, instead of drawing the branch out, it's just C4H9 hanging off the polymer chain. And then we grow a new polymer from that radical that's in the middle. It's a little tricky because I move it around, but basically the new polymer now, because remember, this reaction says we're adding monomer. The new polymer is going to grow from here. And so if we want, we could put the new polymer is going to be this squiggle right here. So we have polymer chain, and then we have this short chain branch, which is exactly the structure I've drawn here. It's just turned around a little bit because it's easier to draw digitally that way. But you want to go back and look at that to make sure you know what's going on with the short chain branch and how to get that short chain branch versus how you get a long chain branch. Yes?
Would it have resulted in just linear polymer? For example, when we add the monomer, why does the radical shift? Is that like always true? Why wouldn't the monomer actually attach to that radical?
Yeah, so most of the time we're minding our own business, right? We're just growing linear polymer, right? Monomers round. But remember, when we make polymers, there's billions and billions and billions of reactions, which means when there's a lot of something happening, side reactions can happen. And so, you don't study a lot of side reactions until you get into practical chemistry systems. Or if you take the next organic chemistry, they talk about major products and minor products. And so the branching is a minor product because there's lots of different things that can happen to the radical. And so this is a small fraction of just growing a polymer chain. So mostly we just grow linear polymer. We just do propagation. We make linear polymers from this and everything's well and good. But every once in a while, the conformation is just right. That polymer's all twisted up and boom, we get chain transferred polymer. So the polymer industry has actually figured out how to steer the reaction conditions to get more or less branching when they need to. So it's part of polyethylene technology because this is the most important polymer in the world. So most of the time, we're just going to have propagation. We're going to make linear polymer. It's going to look like this, right? But if I start to talk about branching, or if I start to talk about chain transfer to polymer, you start to think about this. And this will take some studying. Like I said, there's lots of arrows flying around. We're moving a proton from the growing end back into the molecule. And so make sure that you have these mechanisms and that you can draw them out. And that you know the signatures of intra short chain branches and intermolecular long chain branches. That tells you what's going on. If I say you've only made linear polymer, Is there any chain transfer to polymer going on? You say no, because any chain transfer to polymer is going to give me branching. And so if I tell you that at the end of the polymerization, it's all linear polymer, and I ask you what might have happened, you say, well, there's definitely no chain transfer to polymer if it's all linear. So there needs to be some clue as to what happened with the polymer, so you know the situation to apply. Yes?
Could there be a short branch that is equivalent to a long branch?
I mean,
Like if the,
potentially, but we won't cover those little, if you only added a couple monomers and then something else happened. Yeah, but most of the time it'll be very, very clear what happened. Yeah. Long branches are long. Short branches are only C4 or C5. So when I tell you that short branches are only C4 or C5, maybe C6, why do you know that? What sort of, well, what do you know from organic chemistry where you can say, oh, I think short chain branches are only going to be this many carbons? Go ahead.
Me?
Sure.
Okay, well, just looking at it, it forms a ring shape whenever it backbites, and that's like the more stable numbers.
That's right. Remember, rings of 5, 6, and 7 have little ring strain. Of course, a ring with six carbons in it is the lowest ring strain, so it's more likely to happen, right? It's very unlikely that you'll have 2 carbons in the short chain branch because it's really hard to get the polymer to backbite that severely. It's too much ring strain. And then it's also unlikely that you've got 10 carbons in that backbite because that's just unlikely to happen. The polymer would rather, or the conformation drives the 6-membered or 5-membered ring, not 10, 20-membered ring. That's a good answer. Yes.
I'm a bit confused with the structure produced by the long, the long intermolecular chain transfer. I'm just having trouble where the actual polymer, like where the actual chunk group ends and begins.
Yeah, so go home, write it out, get your colored pencils out, label all the carbons, really study this, and we'll talk about that on Friday. Because you can't just look at this slide and say, oh, I've got it, no problem. Maybe a couple of you can, but I can't. I have to go home, I label the chain ends, red and orange, and then I see where those wind up, and I figure out where all the carbons went, and I draw all the arrows to make sure. So go home and write all this stuff out, because chances are I might ask you to write something like this on the exam, so you're going to have to practice it at home. That's the only way you can figure it out. Yes.
So I guess the main part is we're connecting 2 different polymers for the long branch, right? Because
No. Those 2 polymers do not connect. You transfer the radical from polymer 1 over to polymer 2, and then you grow a new branch off of polymer 2. This is not termination. Remember, you connect 2 polymers when you terminate by combination. But this is moving an active center from one place to the other. There's only one active center in chain transfer, and it just moves from one molecule to the other. You don't connect anything. Yeah. So look at this, look at it in detail, and then ask questions about this on Friday, because this is not obvious. It's something you have to study. All right. So if the active center is transferred somewhere other than the polymer, so remember, the key is chain transfer. It's not termination. So moving radical somewhere else. And that's why we call it chain transfer. This is not termination. And again, don't invent any chemistry that we haven't discussed. I'm basically telling you the basics of how polymers work, and you have some knowledge from organic chemistry, but this is not really, let's think of some new reactions, or let's, I'm going to ask you analytical situations about, this is what the polymer looks like, maybe what happened, but don't try and get fancy while we're still learning the basics here. And so make sure that you know these things, and then you can apply some what ifs in your advanced polymer classes. Okay. So if we transfer somewhere other than polymer, and we can transfer to solvent to monomer to chain transfer agent, etc. We haven't changed. Yes.
So he says that, if you transfer it somewhere, it doesn't affect the skeletal structure, so doesn't it, when you transfer radicals of that, then add a hydrogen in its place normally?
Yes. So, okay. So the only way you affect the skeletal structure is if you have chain transfer to polymer. So when you don't have chain transfer to polymer, basically you have a growing chain. Let me go back to my growing chain here. You have a growing chain and you're going to transfer this radical somewhere. A hydrogen pops on there, or maybe an A or a T we showed. So something quenches that radical and you're left with the linear polymer that's done growing. Yeah, so it could be a hydrogen, or it could be like in this demonstration right here, we have our growing polymer chain. This is the active center. Boom, it grabs the T. So now we have two different end groups, right? We've got our initiator on one end, and then we have our T on the other end, which could be a hydrogen, and then we have our new chain over here. Does that make sense?
Yes, I guess the question is like when it's not polymer, I guess is anything still substituted in the radical place? Like, are we not considering?
This T. Remember, we pushed arrows. So this is a real covalent bond right here. We take this radical, there's one arrow there, or a half arrow. There's a half arrow here, and that makes a covalent bond between the carbon and the T. So that's how you kill the radical, or that's how you transfer. It's not termination. That's how you transfer the radical from the growing chain end. Now we move the radical to A, right?
And would A be a new initiator?
A could be anything that's not a polymer. Yeah. Yeah, so this is an important point. As you're growing a linear polymer, this thing is propagating. And how do you get rid of that radical? You have to transfer that radical, or you have to terminate it. The radical just can't sit there. So you can have termination by combination or disproportionation. Or in this case, we've drawn a chemical reaction where T, which is any sort of fragment of this molecule, could be a hydrogen, quenches that radical based on pushing these half arrows. And then because you take this covalent bond between T and A, and one electron goes one way, one electron goes on to A, that automatically puts the radical on A because it's an unpaired electron. Yes.
So for when this is active center to be transferred, and then polymers will have impact on the skeletal structure, but it doesn't say that for monomer, solvent, or initiator. If you look at the like the TA, you're technically adding that T. So isn't that having that impact on the skeletal structure? You're adding something.
T is not a change in skeletal structure because it's just a low fragment, right? And remember what skeletal structure is. Is it a long chain? Is it a branch? Is it a short chain branch like this? So remember, linear, cross-link, branch, those are skeletal structures. So just clipping on the little T at the end doesn't change the skeletal structure. It just changes the end group. So T here is an end group. No, it doesn't impact the skeletal structure, still linear.
Okay, that makes sense.
Yeah. So the only chain transfer reactions that affect the skeletal structure are chain transfer to polymer. And they don't affect the molecular weight, as I told you. You'll just have to memorize that because it's really hard to demonstrate that. Yes. Yeah. Oh, no question. All right. Okay, so we're going to chain transfer to something else, to solvent, to monomer, to TA, something like that. So we just take our propagating polymer and we move the radical to some other place. And what happens is that as soon as you take that growing chain end that's on a polymer and transfer it to a small molecule, even if it grows another polymer, you've decreased the molecular weight and you've slowed down the polymerization. All right, so we're going to talk kinetics because I know you all really, in addition to organic chemistry reactions, really like to talk about chemical kinetics, but this tells us how fast these polymers are going to grow. All right, So you know that we write our general rate laws like this. And so you know that the disappearance of monomer A with time is written as the differential of the concentration of A over the differential of time. And since it's the disappearance of A, it has a negative in front of it. Same thing for B, because these are reactants. We have a rate constant, and we can track the progress of the reaction by looking at the change in concentration of C over time. Remember, some expression like this is change of concentration of C versus time. So what's happening when we do this is the polymer concentration or the monomer concentration is changing as a function of time because we're making polymer, right? So the whole process we're talking about is going from monomer to polymer, which means the monomer concentration is decreasing and the polymer concentration is increasing. So changing monomer to polymer, which means concentration of monomer is decreasing. So that's how we sort of think about this in the context of what that plot is. So there's other details with writing chemical equations, like what are the rate determining steps and things like that. But this is the basic, and we're going to build this up for the polymer. It's relatively simple. You'll have the equations in front of you. You just need to know how to use them. And so the rate of polymerization is the rate at which monomer is consumed. Remember, square brackets M is concentration of monomer. This is versus time. So we don't necessarily talk about number of molecules of monomer because it's a lot to count. And chemical kinetics is based on concentration because we're going to start moving the concentrations around and see what the effect is on the rate of polymerization. But this is how the rate of polymerization is defined. So if we look at the disappearance of monomer versus time, we can get the rate of polymerization. Is everyone okay with that? All right, that's relatively easy. And so now what we're going to do is we're going to take each of the steps that we just learned about, and we're going to write a rate expression for each of those. So this is going to get a little bit tricky in terms of what process and how we develop the rate expression. But at the end, we'll simplify this to get a really nice expression for the rate of polymerization. And so this helps remind us about the steps that we have to go through to make one of these polymers. And so we have the rate of initiation, right? If we don't have any initiation, you don't get polymer, or you don't get these types of polymers, right? Because we're talking about free radical polymers. And so in initiation, you have step one, which is the decomposition of what's this I species called? What do we call that? The initiator. I don't think we have any other I variables in this class. So I is always an initiator, and it breaks apart. Why is there 2 in front of this R dot? In general, we break an initiator in half and we get 2 initiated radicals from that. We don't really call them I dot because we save I for the initiator itself, but the I basically breaks in half and you get R dot plus R dot. So initiator forms, or initiator molecule forms 2 radicals. And you have to keep those R's separate in your mind from R1, R2, R3 for functional groups in organic chemistry, but that's what we're stuck with. And then step 2, what's happening in step 2? What is the physical process? What is R dot plus M? What's going on? That initiator fragment is reacting with what? The monomer. So remember, M is always monomer. And so this now is ready for propagation. And it just turns out by studying lots of reactions that the rate of initiation equals the rate of formation of radicals, and the rate determining step is the dissociation constant of the initiator to begin with. Because as soon as you have radicals, monomer wants to act. The monomers are reactive, they're going to make polymers. We know that's fast, like a chain reaction. And so we don't need to include step 2 in our kinetic expression because the rate of initiation is dominated by the dissociation of the initiator. And this is concentration of initiator molecules. We have the 2 there because remember, we get 2 fragments. And in this single arrow reaction, Kd is the dissociation constant because that's a rate constant for that reaction. So just like we wrote here, the rate constant K of the reaction of A and B to form C, the rate is dependent on the rate constant times the concentration of the reactants, right? Not the concentration of the products. Same exact thing right here. We have the rate constant Kd. We have the concentration of the reactants. There's just one, the initiator molecule, but we get 2 products. And so we have the 2 in front of there because we get 2 radicals for every one initiated. So that's the rate of initiation. Is everyone with me so far? All right. So there's one more tricky thing for rate of initiation. Not all radicals turn into polymers. And so we put this fudge factor. That's what F stands for. The initiator efficiency. So this means that in some cases, you have an initiator like AIBN. And even though you break AIBN into 2 radicals, not all those radicals make polymer. They can reform, they can do side reactions with the solvent. Bad things happen to radicals because they're really reactive. And so we put this initiator efficiency in there, which just tells us about the percent of radicals that make polymer or start to propagate active centers. And you have to be given this, or you have to be given some hints as to what this number is. Otherwise, you can assume it's 1 and you just write on your paper, I'm assuming initiator efficiency is 1, and that can be a good or a bad assumption depending on what information's in the problem. So this is just something you need to include. It's not a native part of the kinetic expression. Rate of propagation. So this is growing chain end. And we denote it as MI because it's a bunch of monomers connected together. We just don't write them all out, but this is a growing polymer chain because it's got a radical on it, right? This is a monomer. So this is propagating 1 monomer. So we're just going to connect 1 monomer, and then we have a new growing chain end, which is denoted as the degree of polymerization goes up by 1. Here's the radical. New growing chain end. And we have a rate of propagation. And so we have the disappearance of monomer as a function of time is the rate constant times the concentration of monomer times the concentration of growing chain ends. Yes. You will be given information that will lead you to that. Yeah, you can't make up the rate constant. You need some kind of information, or you go need to look it up, and not in this class, but in other classes, you'll have to go look it up. But that rate constant is known for an awful lot of monomers. Yeah, but you'll be given some kind of information. All right, and so that's all propagation is. And so remember, when we talk about propagation, we really have to go back to the basics and say, okay, propagation is just step number 2, taking a growing polymer chain and adding one monomer. That's propagation. Nothing fancy is happening. Nothing weird is going on. You're just adding a monomer, and we talked about head to head, tail to tail, head to tail, all that stuff. That's what propagation is. All right. Rate of termination, of course, we have 2 termination reactions. And you notice, even though termination and disproportionation, you know, there's stuff going on, right? They have exactly the same reactants. 2 growing chains. And they're going to terminate. Haven't talked about chain transfer, right, yet. They're going to terminate. And basically, in termination by combination, you get one molecule with the degree of polymerization of the sum of the 2 growing chains. And in disproportionation, you basically get 2 dead chains, and then you know one has a vinyl bond on it. And so make sure you can connect this picture to this picture right here. Termination, what happens? Only 2 things can happen during termination. This is termination by combination right here. So you take 2 growing polymers and you get 1 polymer with the sum of their molecular weights. And then with termination by disproportionation, you take 2 growing polymers, you kill the radical, you get dead polymers because it's termination. So you have the radical's gone, and you get one with a double bond. So make sure you can connect that process to this little diagram right here and make sure that makes sense to you. So we can write a rate expression for the rate of termination by combination. We can write a rate expression for termination by disproportionation. Notice that they both have exactly the same reactants, and you have 2 different rate constants. So if you combine this expression, here's termination by disproportionation, termination by combination, we can combine KTD and KTC to form KT, termination. KT is overall rate constant of termination. And you know it's just the sum of the 2 different modes. So if I tell you that all of termination is dominated by combination, you know that KT equals KTC, and then disproportionation is 0. That's a lot of T's and C's and everything else. Make sure you write it down. But the sum of the 2 modes of combination or of termination equals the overall termination rate constant. And I will give you a hint as to what mode dominates. Yes.
Why are you lumping the M dot into this?
M dot times M dot is M dot squared.
Yeah, but they're 2 polymers.
They are, and it turns out from the statistics of polymerization that it doesn't matter if we track the degree of polymerization of these separately, because there's a lot of degrees of polymerization. And so we don't have to go through and write a separate expression for each degree of polymerization. Because what is the principle that we talked about where all chemical reactions happen at the same rate no matter what the molecular weight is? Principle of equal reactivity, right? And so this is a little bit of a simplified view, but because of the principle of equal reactivity, we just have to address the reactive species. We don't have to address the molecular weight dependence. All right. So you can get out your clickers. We're in C and D. Great, thank you very much. Okay. we've started making radicals, we've started terminating radicals, we're propagating radicals. And so eventually the rate of formation of radicals and consumption of radicals reaches a steady state. And a steady state means nothing's changing in terms of more radicals or less radicals. So we have an equal concentration of radicals as a function of time. In order to reach steady state, what needs to be true? So remember, to kick off the polymerization, you have to form radicals in the first place. Then they're terminated. You know, they live for a while, then they're terminated. So in order to get an equal concentration of radicals that are living as a function of time, what rates need to be equal? We're at 51, that's perfect. And so one of the big assumptions, great. One of the big assumptions that we make to simplify this is that the rate of initiation equals the rate of termination. And so that means that when we form a radical, we get termination of another radical. It's not the same radical, or else the radical wouldn't grow. So we don't initiate a radical and right away it's terminated because it hasn't propagated. But one of the assumptions we make in order to develop the expressions that I'm going to show you in a second is that rate of initiation equals rate of termination, which means we have steady state propagation of polymer. Steady state propagation. And that's actually why that molecular weight plateau level, that's why I draw it leveled off. That means we're making polymer. As we increase conversion, we're at steady state. Nothing's changing like the molecular weight or molecular weight distribution. That's a detail you just have to remember. All right, this is where I want to get to. I think we have just a couple more slides to go here. But once we write this expression, rate of initiation equals rate of termination, we can write down our rate of initiation. That's great. We can rearrange this expression and we can get an expression for m dot, the steady state concentration of radicals, which you don't know unless you know all these other factors. We control the concentration of monomer by just putting whatever concentration of monomer in the reactor, right? I add 5 molar monomer or I add 10 moles per liter monomer. That's a variable that you have control over because you have a bucket of monomer that you pour in there. You don't have control over the radical concentration unless you're able to control or unless you're able to know all these different variables: the initiator concentration, the dissociation constant of the initiator efficiency, and then the overall KT. Remember, KT equals K termination by combination plus K termination by disproportionation. So this is important. This is the only equation that we have where we can get m dot. There is no other way to figure out m dot, but we can know all of these things, right? We know the initiator and the temperature. We can know KD. We can control the initiator concentration. You have to have some information on F, and we have to have some information on KT, but we can get all these variables. All right. So if we substitute this back in, and this is the last slide, although I think I'm going to do one more clicker because we have a couple more minutes. If we substitute this in to the simple rate of propagation, right? We can look up Kp for whatever monomer we want. We get to control the concentration of monomer, and now we know what the expression for m dot is. And so if we substitute that in, we get this steady state rate of polymerization. So how fast are we turning monomer into polymer? We need to know propagation rate constant, concentration of monomer, and then this, of course, is m dot. So the question is, and this is a lot of the gist of the question that I'm going to ask you on this. Let me stop this. What happens to the total radical concentration at steady state if we double the concentration of initiator? This is our equation for the total radical concentration at steady state, right? M dot is propagating. and we're gonna double the concentration of the initiator, what happens to MDOT? So this is a math question. And so if you take I brackets from 2 to 4, how does MDOT increase? And everyone can ring in. Whoop. It increases by a factor of the square root of 2, because remember, this is in the square root. So that's really important, because I'm going to ask you, this goes up by a certain amount, this goes down by a certain amount. What happens to the rate? What happens to the MDOT? You can check out the homework, come to office hours, and we'll wrap this up on Friday. It'll be a lot of good questions. See you then.